Hello, my name is Tony Lentz with FCT Solder. This is Fill the Void 7, a continuing study of the impact of solder alloy on voiding in solder joints. We presented the initial part of this work at SMT International last fall, where we looked at 5 different solder alloys made into solder paste using the same flux medium for each, and compared the differences in voiding for each solder alloy. I'll give a brief introduction on voiding and why we are interested in it. Talk about voiding and potential reliability concerns in solder joints. Talk about the limits that our industry has on voiding. Get into some overview of root cause of voiding. And then we'll talk about our prior work on the subject. I'll tell you how we set up our experiment to do this test. Then we'll get into the results of overall solder paste reflow performance and then voiding results for these different solder alloys. Then I'll have some conclusions and recommendations. And if you have any questions, please feel free to email me. My email information is on the title slide as well as the final slide of this presentation. So voids can create signal noise like what's shown here. We've got voiding in these BGA arrays. I've heard of this problem at one particular customer that was making monitoring and measuring equipment that was ultra sensitive. I think they were working to the order of like femtoamps or something, really tiny current measurements that they were trying to measure. And voids in the solder joints were creating some noise and interfering with their ability to measure that. Voiding that's excessive, like what's shown here in this QFN thermal pad, could create an overheating situation for the component, and the components might fail if they overheat. And then, of course, voids that are massive, like this void in this BGA, cause the crack in the solder joint. So we do know that voiding may cause reliability risks with solder joints. However, Hillman and his counterparts found no correlation between voiding and reliability for QFNs with 4 different solder alloys, and that was presented at SMT International in 2019. But I have field experience, stories from customers that voiding is related to reliability for some applications. Here's voiding limits from our industry. The main voiding limits are found in J Standard 001, IPCA 610. The limits are 30% max area in a solder joint for BGAs and 50% max area in QFN thermal pads. IPC 7093, which covers bottom terminated components, suggests that less than 30% void area is typical on thermal pads, but it actually refers back to J Standard 001 for the limits. IPC 7095 is the BGA standard, and this was the original standard that had voiding limits published in it, so this is usually what we think of when we talk about voiding limits in IPC standards. This gave a limit of 25% area and less than 50% diameter in class 1 and 2 electronics, and then less than 20% area and 45% diameter in class 3 products. However, voiding limits are often set by end users and OEMs. So regardless of what industry standards are, any kind of an end user or your customer could set a voiding limit that is lower than this. It might be more difficult to meet. So regardless of what the limits are or whether voids actually cause reliability problems, we have to meet limits that are imposed on us by the end users and OEMs. And that's the challenge that most of my customers face. Voiding is normally attributed to gas bubble entrapment, which is influenced by the flux because that has volatile materials in it that have to evaporate during reflow. Solder alloy plays a role, as does solder powder size. Stencil design can influence that, as well as reflow profile, and so on. I wanted to find out how long it took for gas bubbles to leave the molten solder, so I created a simple test to measure that. I placed 20 grams of solder paste into an aluminum weigh dish and then put it onto a hot plate and melted it. And it goes through various stages where initially it starts to look like this, where you've got some gases starting to form as the flux evaporates and the solder is still largely not melted. Then the solder starts to melt around the perimeter, and then a lot of gas is being generated at this stage. And then here you've got fully melted solder, but there's a lot of gas bubbles entrapped in this rough looking solder deposit. And then at the end, the solder collapses and coalesces into a smooth, shiny solder ingot but you've still got some gas here being generated by the flux around it. So I measured the time from initial heating till the time for the last gas bubble to escape for each one of these solder alloys. So the second major cause to voiding is wetting or spread behavior of the solder. And that's influenced by stencil design, by the flux, by the alloy, by surface finish, by reflow profile, and other factors. We made different stencil designs for these QFN thermal pads. We took our standard 9 window pane stencil design and the webs between, or the gaps between the solder paste bricks that are printed, and we varied this. We made a wider gap and then we made some narrower gaps. And then we correlated the gap width along with the solder alloy to determine if those two things together influenced wetting or spread in such a way that voiding was affected. So in prior work, we found that window pane designs minimize voiding, and we were able to vary the number of panes, the web width, the largest perimeter, and so on. And we were able to minimize voiding with some of the window pane designs that we used. We also found that reflow profiles altered voiding behavior. This is pretty commonplace that we go to first when I'm troubleshooting voiding problems. It's easy to change a reflow profile, as you know. It might take an hour or two to finalize a profile and see some results. Different lead-free alloys were tested in the past, and we definitely saw some different voiding behavior, although that wasn't the focus of the paper at the time. So I wanted to study that a little further with a wider array of solder alloys. We found that increasing the area of printed solder paste coverage minimized voiding, as well as increasing the stencil thickness. So in general, more volume of solder paste on BTC thermal pads tends to reduce voiding. We also found that increasing the IO pad volume decreased voiding. That was true specifically for QFNs, where we added solder paste onto the toe of the IO pads outside of the body of the component, and that pulled back and formed taller mounds of molten solder during reflow, which lifts the component up off of the thermal pad, allowing gases to escape. And then those solder joints on the IO pads would spread back out again during reflow, and the thermal pad would come down and make contact with the solder underneath the body of the component, and that decreased voiding. We also saw that different solder alloys showed different voiding behavior with a no clean solder paste in the last paper that was published that I mentioned earlier. And I'm going to continue with that with a water-soluble solder paste in this work, and I'm going to show data from both of these papers. So here's our experimental setup. There are 5 solder alloys that we're studying here. The first one is tin lead as the baseline solder alloy, and that melts at 183 C. The second alloy is SAC305, and that melts between 218 and 219 according to this particular data. Commonly, we refer to that as a 217 to 220 melting range. And then we've got a tin bismuth copper nickel alloy, which has no silver in it. That melts between 221 and 225, but it usually reflows in a standard SAC305 profile. And then we've got a tin silver bismuth copper alloy, which has 3.5 silver, 3 bismuth, and 1 copper. And that has a slightly lower melting range because of the 3% bismuth that's added to it. It melts between 205 and 213 C. And then we compared that to a low temperature alloy, which is a tin 37% bismuth with some additives type alloy, and that has a pretty wide melting range of 139 to 174. But this is the lowest melting alloy in this comparison. So we took each of these alloys and we made a solder paste out of it with the same water-soluble lead-free solder paste flux. This is the test board that we're using for this experiment. This is called a PR test board, and this is the 3rd version of it. We are specifically using these QFNs, these larger QFNs, for voiding measurements. These are QFN 68s with 10 millimeter body size, and the thermal pads are roughly 8.3 millimeters in size. Here's the 4 different stencil designs that we made. The standard stencil design is here. Normally we use a 20 mil web width between the 9 solder paste bricks. We made a larger web, we made a 25 mil web, and then we made 2 smaller webs, 15 and 10 mil web widths. The stencils were all 5 mils thick, and they have 65% area of solder paste coverage. There are patterns on this test board that measure wetting, and we use this to measure wetting or spread of the solder alloy. It's one way to do it. So this has 15 bricks of solder paste printed down each line, and you can see they're closer together in the center and farther apart on the edges. They start with 0.1 millimeter spacing and they range out to 0.4 millimeter spacing. And then after reflow, the pattern might look like this, where you can still see that there's breaks where the gaps were between the bricks. So what we can do is count up the total number of breaks in these solder spread lines and then calculate a wetting or spread percentage. Ideally, there would be completely smooth solder deposits running down the line that had no breaks in it. That would be 100% wetting. Solder balling was measured using these pullback patterns. So we have an array of pads that are 20 mils in diameter and their solder mask up to the edge of the pad, but with a slight clearance. They are not solder mask defined pads. Then we print solder paste over the solder mask with a range of overprints from 500% to 1250%. So pretty large overprint. That largest overprint is a 250 mil diameter dot printed on a 20 mil pad. And then during reflow, they pull back into a sphere. So the solder de-wets off the solder mask. And then we inspect the flux ring for solder balls. So what we're looking for is microscopic solder balling that would be about the size of the solder powder itself. And then we also have a graping pattern, and the graping pattern includes 4 columns of pads that are different designs. So we have circular and square pads, we have solder mask defined and non-solder mask defined versions of these pads, and they range in size from 7 to 12 mils. The area ratio on the stencil is very small. It's 0.35 up to 0.6 area ratio. And graping would look like these yellow circled deposits. So basically when the solder deposit looks like a bunch of grapes, we count that as graping, and where it's smooth, it's not graped. And so we count the total number of graping deposits that we see and then divide that by the total number of opportunities and calculate a graping percentage. So here are the variables that were used for this experiment. We've got 5 solder alloys made up in the water-soluble lead-free solder paste, which I'm coding as WSLF, in an ORH1 classified solder paste. We are comparing this data to the previous study that was with an NC no clean lead-free solder paste, and that happened to be an ROL0 solder paste. So I'll show you data from both of these papers. There are 4 stencil web widths, 10 mils ranging up to 25 mils. We use the SAC-305 ramp to spike profile, which is a standard profile for all the alloys. We ran 20 combinations, so we ran 5 PCBs per combination. Each PCB has 4 QFNs, so we have 20 total void measurements per combination of alloy and web width. And then I ran 2 additional combinations for profile comparisons. So I wanted to see what would happen with the low melting alloys in their normal profile. And then this gas bubble escape test was run with 20 grams of solder paste on a hot plate, and the hot plate was set to 250C for the 2 lower temp alloys, which are tin lead and tin 37 bismuth. And then we ran it at 280C for all the other alloys. The idea here was to keep the hot plate at roughly 50 degrees, 50 to 60C above the melting point of the alloy itself. That was the goal. Here are the printer parameters, pretty standard printer setup. And then here are the 3 refill profiles. So I use the SAC-305 ramp to spike profile for all the experiments, and most of the data I'm going to share is using this profile, which had a time above liquidus of 57 to 59 seconds above 220C, and then peak temp of 241 to 244, and the total profile length was about 4.5 minutes. And then I only ran this tin lead ramp to spike and the tin 37 bismuth ramp to spike profile for those specific alloys, just to compare them to see what would happen versus the SAC-305 profile. All right, here's the refill performance data. This is all in the SAC-305 profile again. So we've got performance metric of up to 100% for each of these on the y-axis. 100% means ideal or best performance. And then the alloys are the different colored bars. So you've got SAC-305 is the green bar, the red bar is tin 37 bismuth, the gray bar is tin lead, then we've got tin silver bismuth copper as the blue bar, and then the orange bar is tin bismuth copper nickel. So you can see graping easy to explain here. This is 100% for almost all these alloys. That means they all had ideal or almost no graping was seen. Wetting showed some differences. So the tin bismuth alloy and the tin lead alloy had 100% wetting or spread, meaning those wetting lines were completely covered with no breaks in the line. All the others showed breaks in the line, and the worst overall wetting on the wetting pattern was the tin silver bismuth copper alloy. In solder balling performance, what I did is I looked at the flux pullback and I evaluated the solder balling and assigned a percentage ranking based on overall how they looked. So we've got some pretty good solder balling or almost no solder balling on the Sac 5 and on the tin silver bismuth copper alloy, and then pretty good solder balling performance with the tin bismuth copper nickel, and then much worse solder balling performance on the two low temp alloys. So the tin 37 bismuth was the worst overall, had the most solder balling, and then the tin lead had second worst solder balling performance. Here's a picture of the solder spread when components weren't placed. So I ran a separate bare board for each one of these combinations of stencil width here on the y-axis and then alloy across the x. And I just wanted to see what would happen with the spread or leveling of the solder on these window paned QFNs. And so that's what I'm showing here. So for example, Sac 305 and the 10 mil gaps completely closed and leveled out all the gaps. 15 mil gaps, you can see some of the brick definition is still here, and then that gets more defined with 20 and 25 mil gaps. So this is showing me that the Sac 305 didn't fully level or spread on 15 and higher mil gaps. The tin 37 bismuth and the tin lead fully wetted and spread. You can see it's very smooth regardless of gap size. The tin silver bismuth copper also shows some brick definition of the 15 mil and higher. And then the tin bismuth copper nickel, I would say 20 mils and 25 mil gaps are the ones that are not fully leveled or spread. So overall best to worst spread, I'd rank them with tin 37 bismuth was about equivalent to tin lead, which had full wet and spread. And then you've got the tin bismuth copper nickel, which was better than Sac 305, and the Sac 305 was pretty similar to the tin silver bismuth copper. Here's that same picture set for the no clean solder paste that we ran previously with the Sac 305 profile. Very similar results here. So the tin 37 bismuth and the tin lead both had full wet and spread on all web widths. And best to worst overall spread, tin 37 bismuth, tin lead were the best. Tin bismuth copper nickel was better than the tin silver bismuth copper, which was about equivalent to the Sac 305. So the worst were the Sac 305 and the tin silver bismuth copper. All right, here's the voiding data. This is voiding by solder alloy, including all web widths and the Sac 305 profile. This is for the water-soluble solder paste. Void percentage area is on the y-axis and solder alloy is on the x-axis. I ran a Tukey-Kramer on a significant difference test to compare the means with a 95% confidence level. Letter codes are assigned, and if the letter codes are different, then these data sets are significantly different. So you can clearly see the tin bismuth copper nickel alloy gave very high voiding, followed by Sac 305, which was statistically lower. And then the tin 37 bismuth and the tin silver bismuth copper were pretty similar in terms of void level. And the lowest overall voiding was with the tin lead solder alloy. This is voiding including all webs in the Sac 305 profile for the no clean solder paste. So this is the same chart as I just showed you for the water soluble, but this is for the no clean from the previous study. And these voiding levels are a little bit different, but they follow a similar trend. Tin bismuth copper nickel still had the highest overall voiding, followed by Sac 305. And then the tin 37 bismuth and tin silver bismuth copper were lower overall, and then the tin lead is tied for lowest with the tin 37 bismuth. Here's the gas bubble escape data by solder alloy for the water-soluble solder paste. So I measured the time for gases to escape from initial heating till the time that the last gas bubble escaped this reflowed solder ingot. Tin lead was the lowest at about 120 seconds, followed by tin 37 bismuth. followed by tin, silver, bismuth, copper, Sac 5, and then tin, bismuth, copper, nickel was the highest. And then I took the mean void area for the water-soluble solder paste off of the slide 2 slides ago and just charted these two data sets against each other. I wanted to see if there was a correlation. And sure enough, I got a pretty good curve fit here. So I've got mean void area plotted against gas escape time, and these dots obviously represent these different data points. The correlation factor here is a 0.98 R-squared value, which is a pretty good curve fit. So it looks like there is a correlation between gas escape time and mean voiding area when you look at 5 different alloys within the same solder paste flux. Here's that same data set from the previous study for the no clean solder paste. Similar trend is seen here. So the tin 37 bismuth and the tin lead had the overall lowest gas bubble escape time and the lowest voiding. Then you got Sac 305 in the middle, followed by tin bismuth or tin silver bismuth copper, and then the tin bismuth copper nickel, the silver free alloy, again had the highest gas bubble escape time and the highest voiding mean area. Here's the correlation curve for that. Again, we get a pretty good line fit with an R-squared value of 0.94. Here's voiding broken out by web width this time. Each box plot includes all the alloys, and this was run with the Sac 305 profile. So this is for the water-soluble solder paste. You can see the letter codes are all identical, so that means these data sets are not different. And you can tell that just by looking at the box plots. These line up fairly well with each other. There's really no difference in web width when all alloys are averaged into these data sets. Here's the similar results with the no clean solder paste. Overall, the voiding's a little lower, it looks like, but still there's no difference between these web widths when all the alloys are averaged into the data sets. Here's the voiding broken out by both alloy and web width in the Sac 305 profile for the water-soluble solder paste. So here you've got the different solder alloys in the major categories here, and then voiding area on the y-axis. And the different colored box plots are the different web widths. So in this case, green is 10 mils, then you got 15 mils is the red, 20 mils is the blue, and 25 mils are the pink boxes. And you can see some differences here in voiding when you break it out by both alloy and web width. Sac 305 has moderate voiding, which changes a little bit with web. It looks like it decreases with increasing web width, which is counterintuitive to me, but that's what the data shows. And then tin 37 bismuth and tin lead both had overall really low voiding that did not vary much with web width. Then you've got tin silver bismuth copper, which has low to moderate voiding, and it looks like it goes down a little bit as the web width gets wider. And then the tin bismuth copper nickel overall had the highest voiding, and again, it doesn't vary much with web width. Here's the statistics on those 5 data sets. So I know this text is really small, so I'm just going to summarize it. First of all, Sac 305 and tin 37 bismuth had higher voiding for the 10 mil webs. That's the only statistical comparison I can make. Tin lead, tin silver bismuth copper, and tin bismuth copper nickel, the 3 on the right, all had voiding that was identical for each of the web widths. So there's no effect of web width on voiding for those 3 alloys. Here's that same data broken out for the no clean solder paste this time from the previous study. So again, there's some trends here. In this case, you can see Sac 305 voiding increases as the web width gets wider. The same thing is true for the tin silver bismuth copper, but these other alloys didn't show that trend. So Sac 305 definitely you get some changes in voiding with web width. Tin 37 bismuth and the tin lead, the 2 low melting alloys, had the lowest overall voiding that didn't change with web. And then you've got tin silver bismuth copper, which changes a little with web. It rises a little bit. And then tin bismuth copper nickel has the highest overall voiding, which doesn't change much with web width. Here's the statistics on that no clean solder paste of voiding by alloy broken out by web width. So Sac 305 and tin silver bismuth copper had higher voiding for the wider webs, 20 and 25 mil webs. So this made more sense to me. This is what I was expecting to see. I was surprised that the water-soluble solder paste did not show that trend. And then the 2 lower melting alloys, the tin 37 bismuth and the tin lead, had low voiding for all webs, which statistically was pretty similar. It didn't change much. There's just some randomness in the data here. And then tin bismuth copper nickel had high voiding for all webs, which didn't change at all by web width. So what I'm seeing here is that really low voiding alloys like these two, the tin bismuth and the tin lead, and then really high voiding like for this tin bismuth copper nickel alloy, give you voiding results that are so low or so high that it kind of takes out the influence of web width. And then these moderate voiding alloys, the Sac305 and the tin silver bismuth copper, do show some difference in web width. And it might have something to do with the metallurgy and how they spread and how they reflow, and particularly how they wet the metals that were used. The test board we're using has an ENIG surface finish, and the components have a matte tin finish. And so how these alloys wet and spread might be a little different for each alloy. Here's a comparison of the two different reflow profiles for the tin lead alloy in the water-soluble solder paste. This was done with a 20 mil web width. So you got a Sac305 profile on the left and the tin lead profile on the right. And what I see here is that tin lead alloy in a lead-free water-soluble solder paste run with a Sac305 profile has lower voiding than when I run it with a tin lead profile, which probably makes sense because this flux was formulated for lead-free applications, not for tin lead applications. The same thing was true for the tin 37 bismuth alloy. When I run that alloy in a water-soluble solder paste, which is a lead-free solder paste, in the Sac305 profile, again, it had lower voiding, it looks like, than the tin 37 bismuth. Although the mean values are pretty similar here, so the comparison here shows that they're pretty identical. Although the box plots clearly show there's a trend, and if I ran more data, I might get better resolution on these box plots, and you'd see an actual difference here. Here's the voiding by profile for the low temp alloys using the 20 mil web width for the no clean solder paste from the previous study. This is Sac305 profile versus the tin lead profile. So you can see again the Sac305 profile gave lower overall voiding than the tin lead profile for this no clean lead free solder paste made with tin lead alloy for this experiment. The same thing was true for the tin 37 bismuth alloy. The Sac305 profile gave lower overall voiding than the lower temp tin 37 bismuth profile. Now I've got a couple of theories of why this is true. First of all, this no clean solder paste and the previous slide with the water soluble solder paste are created for normal tin silver copper type alloys and reflow temperatures. They're created for lead free use, not for tin lead, and not optimized for tin 37 bismuth. So therefore some of the materials in those solder pastes might be lasting a little longer during reflow in a lower temp profile, and therefore gases could be generated a little later during the reflow profile when you run them in a low temp version of the profile. The other thing that might be happening here is these two alloys are the lowest melting alloys in our study, and the reflow temperature of a Sac305 profile is about 240, 245 C, and the difference between that and the peak of the melting temperature of these two alloys is pretty wide, much wider than for any of the other alloys. And so when you heat an alloy after it's already melted, you keep increasing the temperature, the density is going to drop and the fluidity might increase. And so these things might be flowing a little more completely and closing in the gaps. Like the pictures that I showed earlier of the boards without QFNs, they tend to flow and spread very well in a Sac305 profile. So that's one thing to keep in mind with these low temp alloys. If you have the opportunity to run them in a Sac305 profile, that might be a good thing in terms of voiding. You might actually see a voiding reduction with higher temp profiles for these low temp alloys. Although I will say that kind of defeats the purpose of running like a tin 37 bismuth, which is a low temperature, high reliability type alloy. This is designed to run in low temp, and it's mainly used for that purpose in order to reduce temperature related defects on PCBs. So it'd be rare that you'd actually run it in a Sac305 profile. Here are conclusions and recommendations from all of this data. Here's conclusions for the water-soluble solder paste. So we definitely found that gas entrapment and poor wetting spread increased voiding potential for these alloys. Reflow profile influenced voiding for the 6337, but not statistically for the tin 37 bismuth for the water-soluble solder paste. Here's a breakdown of what I saw by alloy and web effect on that alloy. So for Sac305, it overall had moderate voiding, and then it decreased with larger web widths. The tin 37 bismuth had very low voiding, which also decreased with larger web widths. And then the tin lead had low voiding, the tin silver bismuth copper had low to moderate voiding, and the tin bismuth copper nickel had high voiding as compared to these other alloys. And all three of those were not affected by web width. Here's the same set of conclusions for the no-clean solder paste that we ran in the previous study. Gas entrapment and pore wetting spread increased voiding potential for this solder paste as well. Reflow profile had an influence on voiding for both the tin lead and the tin 37 bismuth in that particular solder paste flux. And then solder alloy and web width had an effect for some of these combinations. SAC 305 had low to moderate voiding, which increased with increasing web. Tin 37 bismuth and tin lead had low voiding, which didn't change with web width. And then the tin silver bismuth copper had low to moderate voiding, which increased with the larger web. Tin bismuth copper nickel had high voiding that didn't change with web width. Thank you for your time and your attention and for listening to this presentation. If you have any questions, please send me an email and have a great day.